Welcome to an introduction on the main features of ATLAScan software for the Polaris laser scanner by Teledyne Optech. This is the launcher window, the introductory window we see when we start ATLAScan. From the launcher, we can create or open projects, see and manage recent projects with preview images, statistics, and notes, and exchange objects between them. Work with projects using any of the internal ATLAScan modules, plan, control, process, extract. For example, by clicking on the Stockpile project, it becomes available to open with any of the 4 modules. We can easily switch between the modules using the top bar buttons, or return to the launcher to work with another project. Now, let's create a new project. We are being asked for the project name and the folder in which to place the project. We now proceed to the Plan module, which allows us to plan a scanning survey, upload it to the Polaris, and execute it on the field, assisted by the user interface. We start by creating a new plan. For our assistance, a world map is displayed. Alternative maps are available through the source map options and map type options. First, we import a list of known points in our area, which will be used either as scan stations or targets for backsighting or resection. In this case, we are using WGS84 geographic coordinates in degrees. We need to swap longitude and latitude values by dragging and dropping them. Our points are visible now under coordinates. By double-clicking on any of them we are taken to our area of interest. In this example, our area of interest is the Delphi archaeological site in Greece, and our object to scan is the Athena temple. We decide to use S13 and S16 as scanning stations, while S14 and S15 are used as backsighting targets. Our points have been transferred to the plan. We place the targets under the respective stations. Next, we create a region of interest for each station and adjust the horizontal field of view graphically. We set the other ROI parameters in the Properties window on the right. We could also use the Add Circular Area tool to add an approximate survey station that will be defined in the field by resection. The user is also free to perform additional scans in the field, outside of the plan, if required. Now let's see some other examples in which we will use the Process and Extract modules. Here, we are back to the launcher to select the Open Pit Mine project and activate the Process module. The Process module allows us to import, filter, pre-align and georeference our scans. This project already contains 4 scans of an open pit mine, with fixed verticality, using the Polaris inclinometer, and known scan origins, measured with an external GNSS. In this scenario, which is very common in open pit mine surveys, the alignment and georeferencing procedure is completely automated. All we have to do is run the Align wizard, select the tasks to be performed, skipping importing and pre-processing, which are already done. Select the data type and pre-registration method, edit the constraints, set the known origins with a reasonable tolerance, and start the process. While we wait, it is important to highlight that, in the Process module, it is possible to import, process and merge point cloud data from any sensor or source, which makes ATLAScan a global point cloud processing solution. The Process module uses advanced automatic pre-registration and bundle adjustment algorithms to minimize user intervention and achieve a high-quality final alignment. The full Process module functionality is available in the bundled ATLAScan Works package, which comes with every Polaris scanner. Now that the two-step process has finished, we can view the bundle adjustment report to evaluate the results. We can also load the scans for visual inspection of the alignment. Having aligned and georeferenced our scan data, we can switch to the extract module for post-processing. The extract module varies in functionality between the different ATLAScan packages, Works, Works Pro, Photo and Mobile. Depending on the package, the module can offer a lot of advanced tools, like geometric shapes extraction, meshing and DTM, photo and color manipulation, orthophotos and virtual scans, sections, measurements and notes, inspection, tunneling and more. As the first step in processing our data set, we would like to cluster our 4 scans into a single point cloud. We can then change its colorization according to the inclination, confidence, or altitude. Many other advanced colorization options are also available. For the next step, we create a DTM or topographical mesh using the point cloud we just created, and a polyline feature to be used as a boundary for our DTM. After that we can start the modeling process. The model has been created. After saving it, we will extract the contour lines as horizontal sections. First, we need a reference plane. We use the bottom plane of the model's bounding box for this purpose. Then we have to define the quantity and separation of the contour lines. In this example, we set 50 contour lines, one for every 5 meters of altitude. The generated sections can be easily exported to CAD. With the powerful Edit Mesh tool, we are able, among other things, to automatically extract ridges and valleys, that is, crests and toes, from our DTM, optimizing the result by adjusting various parameters. The output can be saved as a set of polylines in the project. Finally, to close this mining example, it is possible to perform volume calculations between the DTM and a plane. or make cut and fill calculations between two DTMs from different times. Calculation reports are automatically generated in PDF format. Every object in the extract module can be exported in common formats for further processing. Polylines and other vector objects can be extracted as DXF files, models can be output as PLY, OBJ, WRL, 3DS and DXF files, and point clouds can be extracted as E57, LOS, PTC, IXF, or text files. Back in the launcher, we are opening the Flex Building project, which is a 28-scan Polaris survey of a construction site. In this case, the alignment and georeferencing workflow will be slightly different because we do not have coordinates for the scanning positions, but we do have measured ground control points on the project's local coordinate system. Again, we will use the automatic pre-registration. This time we do not use any constraints, except the verticality of the scans, since the Polaris inclinometer was used. We will also set up the final registration using a bundle adjustment to follow. When the pre-registration finishes, the user is asked to confirm the successful pre-alignment as a whole, or confirm each pair of scans separately. After confirming, the final adjustment process starts. The bundle adjustment report, which is created after the process is finished, confirms the high accuracy of the overall alignment. Now, to georeference the scans, we need to identify and pick the ground control points in a scan. This is possible by using an unfolded 2D view of the scan, activated by the Pick Reference Points button under Georeference Tools. We can see the ground control points already picked and we can pick new ones. Alternative colorizations can be applied to facilitate point selection. If circular targets are used, they can be automatically identified by the button at the top left. After picking all the ground control points that can be identified in the scans, we select the scans we want to georeference and activate the point cloud georeferencing tool. Here we import the picked points from all of the scans by clicking Import Targets. Note that if the scan origins were known, they could be used as points for georeferencing too, in which case they would be imported by clicking Import Centers. Finally, in the next window, we have to load a text file with the measured coordinates of the GCPs by clicking Load External Points. And compute registration. Residual errors are colored green or red based on the threshold we set, which helps us discard points from the transformation process if necessary. Finally, we apply the georeferencing transformation to the whole project. We can now load all the scans to visually evaluate the result. We can also switch to the extract module to use any of the available post-processing tools and export the required deliverables. Here is another example of processing in the extract module. this time using the different colorization options for the point clouds. This is a rockfall area on top of a dam, with significant vegetation. We will use the advanced colorization options offered by the extract module to perform an automatic vegetation removal. Using the color mapping window, we can set advanced colorization parameters for the selected point cloud. We have multiple color layers available. For example, we can color by range, reflectance, inclination, etc. In this particular example, we will use the curvature colorization with double thresholding to help us identify the vegetation areas based on curvature. After we adjust the thresholds to define the selection sensitivity, we disable the red interval and exclude the related points. The vegetation points have been removed. Using the cleaned point cloud, we can directly create a 3D mesh of the rocky slope surface and extract the contour lines. In the near future, the extract module will include a vegetation removal tool that will be based on the analysis of the 4 separate laser beam returns that the Polaris can record.